2 of this section of the unit, we want to talk about hybrid orbitals. And if you made it through Vesper theory, you're going to be happy because you already know most of what you need to know about hybrid orbitals. Basically, the atomic orbitals around the central atom in a molecule have to hybridize. And so you may come across a question as part of an FRQ or a multiple choice that say, hey, what kind of, you will predict the shape of the molecule, and then it'll say, hey, what kind of hybridization does it have? All right, so there are 3 accepted types of hybrid orbitals, as well as the ideal bond angles that they produce. Good news, you already know the 3 bond angles, all right? And so if you remember, if there were 2 charge clouds around an atom, CO2 is our common example of that. Okay, 2 charge clouds, we had a linear shape, remember that? What were the bond angles of that? 180 degrees, right? If we had 3 charge clouds, right, we had trigonal planar, or trigonal pyramidal, or trigonal, what do we have? Okay, what are the, 3 charge clouds are, optimal angle was, if you remember, 120 degrees, and then 4 charge clouds, we had our tetrahedral shape, and we had an ideal bond angle of 109.5 degrees. So look at the good news. 2 charge clouds, ideal bond angle 180 degrees. 3 charge clouds, ideal bond angle 120 degrees. 4 charge clouds, 109.5. We have seen those shapes before. And so basically, it's very easy to figure out the type of hybridization if you have the number of charge clouds around the atom. So 2 charge clouds, that's the s and the p orbitals. 3 charge clouds, that's the s and 2 of the p's. 4 charge clouds, that's sp3. So the 3 hybridizations are sp, sp2, and sp3. sp goes with 2 charge clouds, ideal bond angle of 180 degrees. sp2 hybridization, 3 charge clouds, ideal bond angle of 120 degrees. sp3, 4 charge clouds, ideal bond angle of 109.5 degrees. So double bonds here, right? So both carbon atoms are considered to be central atoms here. So each carbon has 3 charge clouds. There's this one, and this one. So 3 charge clouds around each carbon. And so there are sp2 hybrid orbitals. And the bond angles, 3 charge clouds, 120 degrees. And so a sigma bond, okay, a sigma bond results from the direct head-to-head overlap of the orbitals. So, so we have a sigma bond and we have a pi bond. A pi bond results from side-to-side attractive forces between these little unmorphed kind of p orbitals. So all double bonds, anytime you see a double bond, you will have 1 sigma bond and 1 pi bond. Now, something to know, and this is something to tuck into the back of your brain, atoms can spin, right? If this is our single bond, think about structurally, atoms can spin on a single bond, but double bonds are rigid, okay? And double bonds must spin so it must spin together as a solid structure. This looks at cis and trans isomers. If you take organic chemistry, you'll get into this a little bit more. But the thing to remember is that sigma bonds, and I always think of sigma as single bonds, sigma bonds are able to spin on an axis. But pi bonds prevent sigma bonds from spinning on this axis. So double bonds can have cis and trans isomers. So a double bond can only spin if a lot of heat is added to the system. And this is how you get trans fats, which are super bad for you. These are cis and trans isomers of butene. And so notice, I was always taught in organic, cis isomers, the R group, which is something other than hydrogen, is on the same side. So cis is same, and trans, notice these are across from each other. The carbon chain follows opposite sides. So that's a little bit of organic chemistry for you there. All right. Triple bonds. Each carbon has 2 charge clouds. Okay, 2 charge clouds, 180 degrees. What kind of hybridization? We have sp hybrid orbitals. And a triple bond is 1 sigma bond and how many pi bonds? 2 pi bonds. All right. So on a triple bond, the other half of one of the p orbitals is, you can't see it, it's behind. So there are 2 pi bonds and 1 sigma bond. So sigma bonds contain more bond energy. If you look at extended pi bonding, this is benzene, C6H6. It's a ring structure. So electrons are being shared in each pi bond, and if the pi bonds flip back and forth between carbon atoms, the shared electrons can actually be delocalized. That means they can circulate around the structure. So that's why they often use this little third representation for benzene. And we can look at this extended pi bonding to explain resonance in Lewis structures. Looking at polar bonds, right? And when we talked about electronegativity, water is our most classic polar molecule. So shared electrons are going to spend more time around the most electronegative elements in a chemical bond. And if the electrons are there more, that end of the molecule is going to be a little more negative than the other end. And so here's an example of hydrochloric acid. In notation sort of things, you sometimes will see this little arrow. So this tells you that the hydrogen end of this molecule is more positive and the chlorine end is more negative. You will also see this little delta symbol, like partially positive, partially negative. I think our electronegativity value of hydrogen is 2.1 and chlorine is 3. So you can see where chlorine is our more electronegative element. So if a molecule is polar, it must have a dipole moment. Good news, you're not going to make calculations, but you will need to determine if a molecule is polar or nonpolar. So to know if a molecule is polar, you have to know if the bonds are polar, and you have to know the overall shape. So you draw the Lewis structure. From the Lewis structure, you can predict the shape of the molecule. Between the Lewis structure and the shape of the molecule, you should be able to determine if the molecule is polar or nonpolar. I'm going to show you some examples and show you a little trick, kind of. okay? All right, so HCl, let's think about this, okay? Are the bonds polar? Do the dipoles cancel, okay? So for polar molecules consisting of two atoms, the partial negative charge of the more electronegative element is always equal in magnitude to the partial positive charge on the less electronegative element. Since one end of this molecule has a partial positive charge and the other has a negative charge, that makes it polar. If a molecule has a dipole moment, it means it has a positive and negative end. So the bond dipoles do not cancel, so the molecule has a dipole moment. And so for polar molecules that have two atoms, the partial negative charge on the more electronegative atom is always equal in magnitude to the partial positive charge on the less electronegative. All right? CO2. Now, my hint look at the central molecule. If your central molecule does not have a lone pair of electrons, a general rule is that the molecule is nonpolar. I'm hoping this will be helpful. There are some exceptions, and we'll talk about that, like BF3, but we'll talk about that, okay? So basically, our molecule is nonpolar, right? The bonds are polar. The carbon-oxygen bonds are polar, but they are symmetrically arranged. Remember, this was a linear molecule. And so if you're pulling in both directions, it will not have a dipole moment. Now, basically, what you'll have to do as part of your analysis is really determine whether a molecule is polar or not. And again, that general rule, when you look at the Lewis structure, if that central atom does not contain a lone pair of electrons, in general, that molecule is not polar. Okay, so CO2, when you see CO2 in a discussion about everything, remember CO2 is nonpolar. Ozone is though, but we'll talk about that another time. Okay, water. Just looking at the Lewis structure, do you predict? And you should already know, but do you predict, is it polar or nonpolar? So you should say it is polar, right? There's our little oxygen. Oxygen is polar. It has two polar bonds. They are asymmetrically arranged. Remember, this was our bent molecule. It started as a tetrahedron. And then those two lone pairs of electrons really push those hydrogens a lot closer together, and we make a bent molecule. The dipoles do not cancel, so water is probably our most classic polar molecule. All right, look at BF3, okay? Remember, BF3 does not have a complete octet. Are the bonds polar? I think the bonds are polar, right? But our BF3 is non-polar. It has three polar BF bonds, but they are symmetrically arranged around the boron, and so our bond dipoles cancel, no dipole moment. Good news for us, if you do the Lewis structure of BF3, it looks like this, okay? Again, it follows that rule that there is not a lone pair of electrons around the boron, so nonpolar, okay? CCl4, Lewis structure, looks like this. Do you predict polar or nonpolar? It has 4 charge clouds, no lone pairs. Do you remember the shape of it? It should be a tetrahedron, right? And it is nonpolar. So 4 polar carbon chloride bonds symmetrically arranged around the carbon. The bond dipoles cancel, does not have a dipole moment. It is nonpolar. A nice little rule, okay, is that, okay, no lone pair. Now here, notice I have 3 hydrogens, but then I have something different attached. And so if we have the same thing attached, we will be nonpolar. But attaching this chloride makes this molecule become polar. Okay, so polar, the bond dipoles do not cancel, so this molecule is going to have a dipole moment. If all the same things are attached and there is not a lone pair of electrons on the central atom, we will be nonpolar. But in this example, okay, we don't have a lone pair of electrons on the central atom, but it does not have all the same things attached to it. All right, how about this guy? Do you think he's polar or nonpolar? Ammonia. I see a lone pair of electrons, so right away I'm going to say, yep, I bet you that is a polar molecule. And indeed it is. It has 3 polar nitrogen-hydrogen bonds. They are asymmetrically arranged around the central nitrogen. Diatomic molecules, 2 diatomic molecules that contain atoms from the same groups in the same proportions will have the same shape and will be either polar or nonpolar. So think about, if CCl4 is nonpolar, CBr4 will be nonpolar, CI4 will be nonpolar, CF4 will be nonpolar, if you understand that. So this can actually help if you want to be a chemical engineer. It can help chemists make new materials. Replace an element from one group with an element from the same group that you can either get easier or you could get cheaper, right? So it has SiO2, so silicon dioxide can be used to make ceramics, but tin oxide might work just as well or better. So our lecture today talked about sigma and pi bonds. The takeaway from that is to just be able to recognize that a single bond will be sigma bonds, a double bond will be a sigma and a pi, and a triple bond will be a sigma and 2 pi's. And addition of the pi bonds makes that bond shape more rigid. Something that has 2 charge clouds will have sp hybridization. Something that has 3 charge clouds will have sp2 hybridization, and something with 4 charge clouds will have sp2 hybridization. Sp has a bond angle of 180, sp2 has a bond angle of 120, and sp3 has a bond angle of 109.5. And then we can predict if a molecule is polar or nonpolar. Look at the Lewis structure, really. If there is a lone pair of electrons around the central atom, one or two sets, you will be polar. If your central atom is attached to different molecules, you will most likely be polar as well. So armed with this, we should be able to complete all of the homework problems for section 2.7. As always, if you have questions, please contact me. Thanks, guys.